Hi, and welcome to the screencast on membrane potential, or specifically resting membrane potential. If you want to read what the book has to say about it, you can check out chapter 3, pages 70 to 73. Before we can talk about the membrane potential itself, we have to talk about the conditions that make it possible. And one of the conditions that makes it possible is the activity of the sodium potassium ATPase, which, as you can see, pumps 3 sodium out and 2 potassium in for every ATP that it hydrolyzes. So you start here, this is cytoplasm, so this is the inside of the cell. That's the extracellular fluid. The yellow sodium ions jump onto the inside of the pump, and then the pump hydrolyzes an ATP, and using the energy from that ATP, it pumps the sodium out of the cell. Then the potassium outside the cell can hop onto the pump, and then the pump will release the inorganic phosphate that it got from that ATP, and that releases the potassium inside the cell. So you have the sodium potassium ATPase that's busy taking sodium and pumping it outside the cell, and then taking potassium and pumping potassium inside the cell. So then what you end up with is a cell with opposing gradients of sodium and potassium. You're pumping sodium out, so you have high sodium concentration outside the cell, and then you're pumping potassium in, so you have high potassium concentration inside the cell. Okay, so I am going to try and draw a cell here. Here we have a cell, and then we want to remember that we've got a lot of potassium inside the cell with a positive charge on it. Then there's also a lot of anions, or negatively charged ions, inside the cell as well. Let's see, potassium we will draw as, let's say we'll make potassium all of these little red dots, right? Because potassium is super duper small. It's just an ion. And then the anions, most of the anions inside of your cells are actually proteins. So they're rather large molecules that have a negative charge on them. And we'll just draw like a little negative and a negative and a negative and a negative. So you've got small positively charged potassium ions and large negatively charged proteins, so that you have sort of charge balance inside the cell. The other thing that many of your cells have, or I should say that all of your cells have, and let me grab a different color here, is potassium channels. These we are going to refer to as potassium leak channels, and we'll just draw goofy little things in the cell here. So this is going to be a potassium channel, if I can draw. Let me see. CHN, well, that looks awful, but it says channel. Those are potassium channels, and they're open all the time. And what's going to happen is potassium is going to leak out of those channels. So you're going to have a positively charged ion leaving the cell through these leak channels. And what's going to happen then is our anion is going to try and follow the potassium outside the cell. So you need to remember from your basic chemistry that opposite charges attract. So when the positively charged potassium exits the leak channels, the negatively charged anions will try and follow it. So what we have here, I pre-drew a little bit, is you've got positively charged potassium ions are exiting the cell, and they accumulate a little bit on the outside of the cell. They don't diffuse straight away from the cell. And then our larger negatively charged anions try and follow. So I'll just draw a bunch of anions here. Whoops, and they're all negatively charged. So you end up with a bunch of negative charges lined up on the inside of the membrane and positive charges lined up on the outside of the membrane. One of the things you want to remember is that this isn't a complete loss of positive charge with all of the negative charges on the inside of the membrane. In the middle of the cell here, you've still got plenty of proteins and positive ions and negative ions and all kinds of stuff going on. But right along the membrane, you've got a few positive charges that are lined up around the outside of the membrane and a few negative charges that are lined up on the inside of the membrane. And this is where the resting membrane potential comes from. So the way the book has a little slightly better drawing of it, but I like my explanation. So you have the accumulation of positively charged potassium ions on the inside of the cell that are always leaking out of these channels at some small rate. And then the larger protein anions try and follow them, but they get stuck on the inside of the membrane. And so you end up with a little bit of negative charge on the inside of the membrane and a little bit of positive charge on the outside of the membrane. So whenever you have two charges that are separated, or charges that are separated, we call this an electrical potential. In the case of, I'm going to go back one, your cells, the anions can still feel the pull from the potassium, and the potassium can still feel the pull from the anions. They are electrically aware of each other, and that's why we refer to it as a potential, because they're pulling on each other, and it sets up a form of potential energy where the potassium wants to a certain degree to come back inside the cell. So when charges are separated by a membrane, we refer to this as a membrane potential. So one of the things that you want to remember, whether we're talking about a muscle cell, a neuron, or any cell in the body, is that all of your cells have a sodium-potassium ATPase. All of your cells have these potassium leak channels. So all of your cells have a resting membrane potential that is slightly negative on the inside. And then just to review some terminology, if you have a separation of charge where it's negative on the inside, we could diagram it like this. If it's positive on the inside, we could diagram it like that. So when we're talking about membrane potential, we refer to what's going on the inside of the membrane. If you have a situation where there's a negative side and a positive side, then this is referred to as polarized. If the inside of the cell is negative, or not the inside, but the inside of the membrane is negative and the outside of the membrane is positive, it can be said to be polarized. If you move towards the middle in either direction, then that is becoming depolarized. Now your cells are resting. Their resting membrane potential is somewhere between negative 70 and negative 200 millivolts, depending on which cell it is. This cell here we're saying is resting at negative 100 millivolts. If it moves towards zero, we call that depolarization. If it moves further in the other direction, you get more accumulation of negative charge on the inside. That's referred to as hyperpolarization. So all of your cells are always a little bit negative on the inside. If they become less negative on the inside, we call that depolarization, or becoming depolarized. If they become more negative on the inside, then we say they are hyperpolarized. So that is the forces behind the resting membrane potential. I hope it makes sense and that you have had as much fun watching it as I have had making it.